Introduction to Neural Networks with C#, Class 7, Part 1. Welcome to Class 7. In this class session, we're going to learn about simulated annealing. Simulated annealing is another way of training feed-forward neural networks. We've already learned about backpropagation and genetic algorithms. Simulated annealing is the third way that we will learn about in this course to train a feed-forward neural network. Simulated annealing works by simulating the metallurgical process of annealing. When steel or other materials are being created, they will heat the metal to a very large temperature and then allow it to cool in cycles. This causes the crystal structure of the metal to create itself in a more organized way. We do a similar process in computing technology. We represent the solution to a problem as a series of numbers, just like in a genetic algorithm. You think of it as a long string of numbers. Then you take those numbers and you excite them with heat, or synthetic heat anyway. You basically randomize them in a very specific way, and you allow that randomization to cool off as the temperature decreases. And this generally leads to a more stable solution, or a better solution. We can apply simulated annealing to the traveling salesman, just as we did genetic algorithms. And one of the examples in this chapter does show you how to apply simulated annealing to the traveling salesman. You can also apply it to training neural networks. It's actually a very effective way of training a neural network. Simulated annealing is also faster to solve the traveling salesman problem than is the genetic algorithm. We will look at exactly what simulated annealing is in this part, and in the other parts of this class session you will learn how to implement simulated annealing and make use of it in your own programs. We begin by examining how simulated annealing works. Simulated annealing is based on the real-world metallurgical process of annealing. Annealing is used in steel processing. When steel cools, it tends to crystallize better if it is cooled slowly and over several cycles. This allows the crystals to form uniformly. Computerized simulated annealing works very similar to the actual annealing process. There are three variables that we must pass the simulated annealing algorithm. We give it a starting temperature and an ending temperature. Just as temperature in the real world refers to the excitement level of the molecules in a substance, the temperature in the simulated annealing process refers to the amount of randomization that will be applied to the solution that is being evaluated. We also look at how many cycles of this temperature change occurs. Throughout these cycles, which execute every iteration, we proceed from the starting temperature to the ending temperature. The more cycles, the more slowly that the algorithm can cool. However, the more cycles, the longer it takes to execute an iteration. Let's look at the flowchart for a simulated annealing process. This flowchart continues on to the next slide. You're seeing just the top half right here. First, the algorithm starts. We are going to randomize the potential solution according to the current temperature. This will initially start out at a higher temperature and proceed to a lower. We evaluate whether the randomization produced a solution that is better than the current solution. If the solution produced is better than the current solution, then this solution that was just randomized becomes the current solution. Then we see if we've reached the maximum tries for this cycle. We continue looping if we have not. We keep applying the randomization until such time as we get a better solution than what we had previously. This will continue till we reach this maximum. Then we decrease the temperature by the specified rate. We check and see if the lower temperature bound has been reached. Once we've reached the lower temperature bound, we are done with this particular iteration, and we can stop. Again, this is one iteration only of the simulated annealing process. Just as with backpropagation and also genetic algorithms, we may progress through many iterations or epochs before we decide that we've reached a suitable solution. And just like with genetic algorithms and backpropagation, we can set up a loop to continue looping through iterations of the simulated annealing algorithm until the overall error for the neural network has dropped below a certain acceptable percentage. Or we can loop over a fixed number of iterations too, if desired. Either works for this algorithm. So far in this course, we have learned 3 learning methods that can be applied to the feed-forward neural network: backpropagation, genetic algorithms, and simulated annealing. You may wonder when you should use each type. Basically, some types apply better to different types of neural networks or different solutions that the neural networks have been created for. Backpropagation is sort of the standby that you use in feed-forward neural network programming. However, sometimes it will reach a problem called the flat spot problem, where it simply does not seem like it's progressing with its learning. Simulated annealing can be then applied for a few iterations to kind of shake things up and get backpropagation over the flat spot. Genetic algorithms can be used sometimes when you don't necessarily have a complete solution set, but you can evaluate each individual solution, like tic-tac-toe that we looked at earlier. This concludes part 1. In part 2, you will learn how to actually implement simulated annealing in code. Part 3 will continue by showing you how to actually make use of what you implement in part 2. We hope you will continue with part 2. Thank you. This course is based on our Introduction to Neural Network Programming books for Java and also Introduction to Neural Networks for C#. Available in both paperback and ebook format.